Let's continue chapter review, chapter 15, multiple integrals. In this chapter, I selected also 3 sections. Let's see the first one, double integrals over general regions. Multiple integrals can be evaluated with iterated integral, where the given domain must be covered once and only once, without missing and without overlap. Also, you should be able to change the order of integration correctly. Find the volume of the solid that lies under the plane z equal 1 plus 2i, and above the region D in the xy plane, bounded by y equals 2x and y equals x squared. Let's try to recognize the region. Okay, that is x-axis, that is y-axis. Y equal 2x, that one. So that is y equal 2x. And y equal x squared. That is like that. That is now y equal x squared. Bounded by these two, one is line and the other one is curve. That region is D. And in the region, the solid has height 1 plus 2i. So the volume must be evaluated through integral over d. The height is now 1 plus 2i and dA. Now, for this integral, we have to access the domain. Now, let's try to figure out the domain a little bit more. Okay, we have to find that one and this one. Now, y equals 2x and x squared, so 2x equals x squared, which means that x is 0 and 2. This is 0 and that is 2. X is 2, then y must be 4. Right? Okay, so once we choose x as outer integral direction, then x is moving from 0 to 2, and now y is from there's bottom y to top y. For each x, we are accessing vertically. Bottom y is x squared, and top y is 2x. And integrand is 1 plus 2y, and inner integral is y direction, and outer integral is now x direction. You can get it easily. Now, here, now it is asking this one, try for both orders. Okay, let's consider the other order, which means that y is outer integral. Then y is moving from 0 to 4, and there must be dy. Okay, for each y, now x is moving from here to there. There's bottom x, top x. Bottom x is, okay, x equal y over 2. Y over 2. And top x, that is from here. Now, that one we can see there's x is square root of y. And because it's positive, so that only we are choosing taking positive square root of y. And the same integrand 1 plus 2y and dx. So these are iterated integrals, and you can evaluate. Not so hard, and you can do it yourself. The answer from both of them must be 28 over 5. Okay? Evaluate the integral by reversing the order of integration. Currently, for this one, if you try to do x integration, then not easy. So let's try to reverse the order of integration. In order to do that, we have to recognize the region D. Okay, here this is xy coordinates. Okay, now that means here y is from 0 to 4. Okay, that is 4. And this inner integral means that x is from square root of y to top x is 2. Right? So this one is the same as x squared equal y. Right? So here, okay, anyway, now the curve will be made in this way. Along with that, it's made that way, like that. Right? And now, from here, top is 2. So we have now 2. X is moving. That is bottom y, bottom x. And it's the same as x squared is y. So this is for each y, bottom x to top x. So it is covering that way horizontally right now. So that's D, right? Now, how about the other direction? Then there must be x is from 0 to 2. Now, we are accessing this region vertically. Okay, y is, bottom y is 0. Top y is, now there's y called x squared. Top y is x squared. Right? Now, there is e to the x cubed and y direction, inner integral and out integral. Okay, this is y independent, so we can get it immediately from 0 to 2 x squared e to the now x cubed and dx. Okay, now we can get antiderivative, which must be 1/3 of e to the x cubed, right? And we are evaluating from 0 to 2. So there's 1/3 is there, x is 2, then that is e to the 8, x is 0, then e to the 0, which is 1. So we can get this answer, okay? So sometimes we have to reverse the order of integration, and with that we can solve the problem. This problem is not easy to get with this order, but after changing the order, you can get it. Okay. Now, sketch the region of the integration and change the order of integration. You can do it easily. X is, okay, for that one. Now, x is moving, okay, y is moving from -2 to 2. And that means now x is bottom x is 0 and top x is here square root of 4 minus y squared. Okay, this one is the same as by squaring we have x squared plus y squared equal 4. Of course here x must be not negative, but this is a circle of radius to right side. So that's the reason. Okay, and you can access now here horizontal, okay, vertically. Right now it's horizontally, so you can access this vertically. So you can do it. And how about that one? Okay, y is moving from 0 to logarithm 2. So let's try to visualize it. 0 to now logarithm 2. That's in the y direction. Now that means this one is bottom x is e to the y to top x equal 2. Now that one is the same as y equal now logarithm x. Right? So logarithm x, and it's given in this shape. Okay, it's a passing one, and like that. So here top x is 2, so that we have now is 2. At 1, the value must be 0. Now, this integration is done y is moving from here to there, and that is a bottom y, bottom x. This curve makes a bottom x, and that is top x, so that it is accessing the domain horizontally like that. Now, if we try to get x out integration, then given integral must be from 1 to 2 in x direction. In y direction, that is bottom y is 0, top y is logarithm x. And f is there, and now dy and dx, right? Okay. Now we'll move to section 15.7, triple integrals in cylindrical coordinates. Cylindrical coordinates along with polar coordinate in 2 directions, and the other direction is straight. There is a formula for cylindrical, the polar coordinate to, in fact, the cylindrical coordinate to rectangular coordinates. X is r cosine theta, y is r sine theta, and z is the same as c. And the other directional transformation can be found along with that. R can be found from this equation. And also we can find the theta. Tangent theta is y over x, and z equals z. Okay. When we try to solve a triple integral with cylindrical coordinates, then the cylindrical domain must be separated into 2 portions. One is polar region, the other one is the orthogonal direction. So we'll see here one example. Okay. Now, evaluate this triple integral with integrand y, where is a solid that lies between cylinders, radius 1, vertical cylinders, radius 1, now radius 3, and above the xy plane and below the plane, z equal y plus 3. Okay. If we try to visualize, then here we have 2 cylinders. One is radius 1 cylinder, the other one is radius 3 cylinder. So we have that cylinder and cylinder, and now they're on, okay, like that. And between these 2 cylinders and above the xy plane and below, z is y plus 3. Okay, that is a plane cutting this way in xy direction is the same, so that now this height is 3. Anyway, we can see the volume below and between these cylinders. We have to find that. Okay, that is region, third region E. Okay, so the given integral must be, now there is 2-dimensional region, there is D, integral over D, and Z direction, bottom is 0, top is y plus 3. And we have here y, and there is dz and dA. Right? Okay. Now there is a z dependent, so it's the same as integral over d, and that is now y times y plus 3, so that is y squared plus 3y and dA. Now we are focusing on d, and d is given in this way. There is circle of radius 1 and circle of radius 3, like that. There's 1 and 3 in xy domain. There is d. So it is a polar region. angle is from 0 to 2 pi, and r is from 0 to, not 0 to 1 to 3. Right? Radius 1 to radius 3. And then y is r sine theta, so the r squared sine squared theta plus 3 is r, y is r sine theta, and we have to put r, the scaling factor, and dr, the theta. Okay, we may consider this one separately. So for example, for that one, along with r, it's separable. And sine theta from 0 to 2 pi will make 0 because it's halfly positive, halfly negative. So that eventually this term will make no contribution to the integral. So we can eliminate. So remainder part is here. The other part is also separable. That is from 0 to 2 pi and sine squared theta and d theta. And integral from 1 to 3, we have r squared r, so that there is r to the 4, no, r to the 3. Okay, there is r to the 3 and tr. Okay, that one, for sine squared theta, we can use a formula half. Okay, that one is same as half and 1 minus cosine 2 theta. Now theta is moving from 0 to 2 pi. 2 theta is moving 0 to 4 pi. So that this term will make 0 contribution. So we can ignore. So remainder part is only half. So from the first integral, we have pi. Okay. From second one, there is 1/4 of r to the 4. Now there is 1 to 3. So that is pi over 4 for the constant. That one will be 80 minus 1. So that is 40. So we have 10 pi. The 40, 80, okay, there's 20 pi. Right? We have the final answer, 20 pi. Okay, now let's see this one. Use the cylindrical coordinates to find the volume of the solid E that is enclosed by cone and sphere. So let's try to visualize it. Okay, we have here the XYZ coordinates, and there is a sphere of radius square root of 8, like that. And then we have a cone with a 45-degree angle. So the cone is given. So now we want to find the volume of the solid E that is above this cone and below of that sphere. So we have to find the volume of that solid. Okay. Now we have to use cylindrical coordinates, which means that the region must be separated into two parts, and so that we may try to find the D. Okay, let's try to use red pen. Yeah, project that one on the XY plane. Then there is now D, and then in Z direction for each point XY, and there's bottom and there's top. So we can access from bottom to top. So the volume must be integral over D, and bottom is from Z is now square root of x squared plus y squared. And top is from here, z equal now 8 minus, okay, x squared and minus y squared, and we take here square root like that. Okay, so top z is square root of 8 minus x squared minus y squared, right? And integrand must be 1, that's z direction and dA. Right? So because it's 1, you can see here that is integral, double integral over d, and square root of 8 minus x squared minus y squared, and minus, and square root of x squared plus y squared dA. Now we have to understand d. Okay, that one, it looks like a circle. And so there is a disk. What is the radius? We have to figure it out from these two equations. Okay, now z equal square root of x squared plus y squared means that z squared equal x squared plus y squared. And then now x squared plus y squared plus z squared, that must be, now z squared is x squared plus y squared, so that is twice of x squared plus y squared. Now that one is 8, which means that x squared plus y squared equal 4. Okay, we have here radius 2. Right? And d is whole disk, so that angle must be from 0 to 2 pi, r must be from 0 to 2, and the first one is now, okay, square root of now 8 minus r squared, and second one is minus r, and we have to have here another r, dr d theta. Right? Okay, so okay, for theta direction, we can get the integral immediately. That's 2 pi. And okay, let's rewrite this one from 0 to 2, r square root of 8 minus r squared minus r squared dr. Okay, that is 2 pi. And then its antiderivative must be a minus r squared to 3 over 2, and along with some coefficient. Okay, once you try to make a derivative, then now 3 over 2 will go out and minus 2r, so that eventually minus 3 will be extra. So we put here 1 over minus 3. Okay, so that is antiderivative. And from this one, now 1/3 and r cubed, and we are evaluating from 0 to 2. Okay, now here 1/3 can go out, so that 2 pi over 3, and from this one, now along with that negation, we have first try 0, then here that must be, okay, 0, then 8, here 3 over 2, that is 1, and once it's 2, then it's 4, so that is minus 8, and this one will be again 1/3 is already gone, so that will be 8. Now 8 can go out, and then okay, here this term is the same as 8 times square root of 8, which means 16. Okay, that is 16 square root of 2 minus 16. Okay, 16 can go out. So the 32 pi over 3, and this is square root of 2, that is 1. Okay, so that must be the final answer. Okay, is it correct? Yeah, is correct. Now, change of variables in multiple integrals. That is really important section. You have to understand this one very deeply. Now, change of variable is a transformation from the pre-domain to R. Your integral is given along with the region. You have to find the pre-domain Q such that that is transformed and one-to-one and differentiable. The C1, so after first derivative is continuous and must be one-to-one. You have to access the domain once and only once, and also when you try to get integral over Q, you have to access this one once and only once, so that the map must be one-to-one. Okay? Now, when you do that way, then x is a function of uv, y is a function of uv. So you can get the Jacobian, the determinant of x uv derivative, y uv derivative, which is this one. In integration, and that is a scaling factor. Originally, you have to get integral over r. Now, the integral is changed to over q. Now, that is a kind of a scaling factor of the regions. That is this times larger than that one. And so you have to put this scale. That is absolute value of this quantity. Okay. Okay. Let's try to solve some problems here. Make an appropriate change of variables to estimate the integral. Here R is region in the first quadrant bounded by the ellipse. Yx squared plus 4y squared is 1. Okay, right now the region R is given in this way. Once you, from this one, divide by, for example, 36, then you can get x squared over 4 equals, now y squared, plus y squared over 9 equals 1 over 36. Okay, so that the region R is given ellipse with the 1.5 times longer vertically like that. Okay, that's R. Over R, you have to get this integral. But for this one, not easy. So we have to change the variable. For example, rather than this region, let's try to make really circular region. In order to do that, we may consider from here anyway. Now, if we choose u equal 3x and v equal 2y, then that becomes u squared plus v squared. Also, this becomes here u squared plus v squared equals 1. But this is not a map. In fact, xy must be expressed as a function of u and v. So from here, the map is x equal divided by 3, u over 3, and now y must be here v over 2. And then from here, now the Jacobian is determinant of x u derivative 1/3 and 0, v derivative is 0, and x, u, y, u derivative is 0, v derivative is 1/2. So that the determinant is 1/6. We found the scaling factor. Now, along with that math, we easily see that here the predomain Q is a circle of radius 1 in UV domain. Okay, that is 1, and that is now U direction, V direction. So mapping is from here to there. There's Q, right? Okay, so the given integral is the same as now integral over Q, and we chose here 3x, 2y to be u and v, so that is same as sine and u squared plus v squared, right? And then here scaling factor 1/6, we have to put that on here, and du dv, okay? It's a polar region. Angle is from 0 to 2 pi, and r is from 0 to 1. That is a sine r squared, and we have 1/6. And now we have to put r and dr, d theta. Let's put the constants outside, okay? So here, that is now theta independent. So in theta direction, we have 2 pi with 1/6. We have pi over 3. And we have to get integral for that one. Okay, what is that? That is minus cosine and r squared. And if we put here 1/2, then it's antiderivative. Okay, that is antiderivative. We have to evaluate this one from 0 to 1. Right? Okay. Just a moment. Okay, I'm sorry. In the beginning, okay, there is a first quadrant. So that is R. I'm sorry about that. And that must be Q. So here also, rather than this one, this is pi over 2. Okay, first quadrant. And that is now pi over 12, right? Okay. So we reach at pi over 24, and then with this one, 0 evaluation is 1, and now cosine 1. Okay, and that's the answer. Okay, I forgot that one. Okay. Okay. Now that's the end of chapter 15. We'll continue for chapter 16 in the next video. Okay, thank you.